Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakalyan. The session number 53 of Graph Theory 2. Now the title of the topic is Directional Duality and Acyclic Digraphs. So what are the ideas of directional duality and acyclic digraphs? We will see in detail. Okay. Now, what is the directional duality and acyclic digraphs? Before that, we think of definition of a converse digraph. Converse digraph, very interesting concept. Converse digraph. The converse digraph D dash of a digraph D has the same vertices as D. So, like the complement of a graph, vertices are same in G and G bar, like that. The converse digraph D dash of D has the same vertices as D, and the arc UV is in D dash if and only if the arc VU is in D. Like that, it is similar to the complement of a graph. Two vertices are adjacent in the complement if they are not adjacent in G. Like that. Don't compare exactly the same concept, just the comparison, okay? Exactly, it won't be the same here in case of directional digraphs, okay? So the converse digraph D dash of the graph D has the same vertex set as that of the digraph D. But how about the edges in D dash? The arc UV is in D dash if and only if the arc VU is in D. If VU is in D, UV will be in D dash. Okay, so like that, the whatever the graph you are getting, that digraph will be considered as converse digraph. Now, how to construct the converse digraph? What you have to do? The converse digraph D dash of a digraph D is obtained by replacing, or you can say by reversing the direction of every arc of D. Very interesting. Same digraph you have to consider, because I know same digraph, vertices will be same. What you have to do? Just you have to reverse the direction of the arcs. If you reverse the direction of the arcs, the resulting graph will be definitely converse of the digraph, isn't it? Because UV will be an arc in D dash if VU is an arc in D. So that's why it is very easy to form the converse of a digraph. The converse digraph D dash of a digraph D is obtained by reversing the direction of every arc of D. So we have already encountered other converse concepts such as in degree, out degree, and these concepts concerned with the direction are related by a rather powerful principle, and this principle a classical result in the theory of binary relations. Okay, so what is that concept we will see here? The principle of directional duality. What is that? For each theorem about diagrams, whatever may be the theorem, whatever the theorem you are getting in the diagrams, for each theorem about diagrams, there is a corresponding theorem obtained by replacing every concept by its converse. So interesting. Those who are interested in research, what you have to do? You consider any concept in diagrams, then reverse the direction of the edge. So you are getting a new digraph, that is the converse of the digraph. So here important idea is that for each theorem about digraphs, whatever the theorems you have got, the results you have got in digraphs, there is a corresponding theorem definitely obtained by replacing every concept by its converse. So whatever the concept we have got in in digraphs, just reverse it. You will get another digraph which is called a converse digraph. You will get related results on the converse digraph. Okay, so that principle is called principle of directional duality. Okay, now what is acyclic digraph? Cyclic, acyclic, cyclic. So it has got a cycle. Acyclic, there is no cycle at all. An acyclic digraph contains no directed cycles. That is the difference. An acyclic digraph contains no directed cycles. Okay, because we are discussing about the directed graphs. So that's why there is no directed cycles. Then that digraph is called acyclic. Okay, now we'll consider one important result. What is that? An acyclic digraph has at least one point of out degree 0. So whenever you consider a acyclic digraph, there will be definitely at least one vertex whose out degree is 0. What do you mean by out degree? You know, the edge which is out of that vertex. How many edges are out of that vertex, that will be out degree. How many vertex are into the vertex, that will be in degree. Okay, so whenever you consider an acyclic digraph, definitely there will be at least one vertex whose out degree is 0. Okay, so now we try to prove this result. Consider the last vertex of any maximal path in the diagram. Point, or you can say vertex. This vertex can have no vertices adjacent from it, since otherwise there would be a cycle or the path would not be maximal. Okay, I think you have followed this. So this point can have no points adjacent from it, since otherwise what happens, there would be a cycle or the path would not be a maximal. Definitely there will be a cycle or a path, you would not be a maximal one. Okay, so then what happens, because we are considering any maximal path, if that is the case, the dual theorem follows immediately by applying the principle of directional duality, in keeping with the use of d dash, that is finding the converse of the digraph d dash. To denote the converse of digraph d, we shall use primes to denote dual results. Okay, so this is the simple theorem. You can write the proof in a simple form also. Okay, so similarly we state the following theorem. What is that result? We will see. An acyclic digraph d has at least one vertex of in degree 0. Like we have got one result, previous result, there is at least one vertex of out degree 0. Similarly, in an acyclic digraph, there will be at least one vertex of in degree 0. So, so what you can say, you can prove in the same fashion how we have proved the previous result. Okay, so it was noted that the condensation of any digraph is acyclic. One observation we have got in the condensation of a digraph. The condensation of a digraph is acyclic, and the preceding results give some information about acyclic digraphs. So if you compare that and the results, what you will get in your mind? So that will be, we now provide several characterizations based on these results and the previous ideas. So what are those? The following properties of a digraph D are equivalent. We are not going to prove the results, just on the basis of observations. These are the results. Okay, D is acyclic. It implies the condensation D star is isomorphic to D. It implies every walk of D is a path. So the following properties of a digraph are equivalent. If D is acyclic, then the condensation of D star is isomorphic to D. Then if it is so, then every walk of D is a path. Okay, so this is one result. No need to prove the result, just on the basis of observation you can state this result. Okay, so two dual types of acyclic digraphs are particular interest. A source in D is a point which can reach all others. A sink is the dual concept. A sink is the dual concept. You know the concept of source and sink. An out degree is a digraph with a source having no semi-cycles. An in tree is its dual. So, okay, so these ideas you can see in the figure 5. See, here there is an example, an outer tree and the converse inner tree. Same graph, same vertices. You have to find the converse of the graph. Okay, so in the converse of the graph, what you have to do, just redirect, opposite direction is given to every edge, so you will get another graph that will be the converse of the digraph. So an out tree and the converse is in tree. So this is one example, very interesting, you see. Yes, same graph, same vertex set, but the direction of the edge are replaced. That is opposite direction. Okay, so the resulting will be the converse of the digraph. So with this we see one result. Okay, a weak digraph is an out tree if and only if exactly one point has in degree 0 and all others have in degree 1. See, we can see the diagram. An out tree, an out tree. A weak digraph is an out tree if and only if exactly one point has in degree 0 and all other vertices have in degree 1. You can see the diagram here. In degree 0 and all other vertices have in degree 1. Okay, so another theorem, a weak digraph is an in tree if and only if exactly one point has out degree 0 and all others have out degree 1. Similar to the previous result. Okay, in tree, out tree. So you can see these are the characterizations of in tree and out tree. Okay, just on the basis of observation we can verify these results. Now next we will consider some digraphs which are closely related to the above. Okay, so what is that concept? We will see a functional digraph. What would be the functional digraph? See, outer tree, in a tree. So like that, a functional digraph is one in which every point has out degree 1. Very interesting. A functional digraph is one in which every point has out degree 1. It implies there will be exactly one edge which is out of the vertex. Okay, so that you can see here. Another concept is a contra-functional digraph. What is it, a contra-functional digraph? A contra-functional digraph is a dual. It is a dual. So you know the concept of a dual of a digraph that already we have discussed. Now we will consider one example here. In this figure, a weak functional digraph is shown. So why it is called a functional weak? Weak because there are three concepts: weakly connected, unilaterally connected, and strongly connected. Weakly connected means a semi-path. Unilaterally connected means there is a path from one vertex to the other, which you are considering the pair of vertices. Strongly, there will be u to v and v to u. So in this graph, you can't see such a path. You will see only the semi-path between two pair of vertices. And it is a functional digraph. Why it is a functional digraph? If you see one, if you observe the degrees of the vertices, every vertex has out degree 1. Every vertex has out degree 1. So that's why it is a functional digraph. Again, it is a weak functional digraph because there is no any path between two pair of vertices. Only semi-path will be there. Okay. Let us consider some other ideas. So now, based on these concepts, so we state one theorem. What is that theorem? It states that the dual what we have provided is a structural characterization. So the theorem is equivalent for a weak digraph D. What is that? The following are equivalent for a weak digraph D. D is functional. What is functional digraph? Already we have discussed. D is functional. Then D has exactly one cycle, the removal of whose arcs results in a digraph in which each weak component is an in tree with its sink in the cycle. You should remember all the areas: sink, source, functional, converse, all those components. What you mean by the component? Then only you will come to know the theorems properly. Okay, so D is functional, then D has exactly one cycle, the removal of whose arcs results in a digraph in which each weak component is in tree, outer tree, in tree, with its sink in the cycle. Okay, so D has exactly one cycle Z, and the removal of any arc of Z results in an in tree. Okay, so to understand these theorems, you must have the terminology of directed graphs, what we have discussed so far. Every time we cannot recall what is the sink, what is the source, and like that. Okay, so if you remember, or if you could understand all the concepts properly, then very easily you will follow this statement. No need to prove the results. Okay, without proof we have just stated these results. Now the another concept is point basis of a digraph. What is the point basis of a digraph? A point basis of a digraph D is a minimal collection of points from which all points are reachable. Okay, reachable. If I say there is an arc AB, AB is an arc, AB is an edge, then AB is an arc, it implies B is reachable from A. Okay, that idea you should remember. If AB is an arc, say suppose E equal to UV is an arc, E equal to UV is an arc, okay, UV, U to V, then V is reachable from U. Okay, that idea you should remember. So what do you mean by reachable from a vertex? If there is an arc UV towards U to V, then V is reachable from the vertex U. So a point basis of a digraph D is a minimal collection of points from which all points are reachable. Okay, all points are reachable. Thus, a set S of points of a digraph D is a point basis if and only if every point of D is reachable from a point of S. Every vertex of D is reachable from a point of S, and no point of S is reachable from any other. Okay, so then it is called a point basis of a digraph. So with this concept we consider one result. What is that? Every acyclic digraph has a unique point basis consisting of all points of in degree 0. Understanding is very simple here. Every acyclic digraph has a unique point basis consisting of all points of in degree 0. I think you are getting all these ideas in your mind because you have got the clear picture about in degree 0, what is the point basis of a digraph, then what is acyclic digraph. If you observe all those terminology of digraphs, then the statement is very easy to follow. Based on this theorem, there is a corollary. What is that corollary? Every point basis of a digraph D consists of exactly one point from each of those strong components in D, which form the point basis of the condensation of D. Okay, so this is based on the main result. Now, what we have considered a point basis. Based on that concept, there is another concept called one basis. So what is one basis? One basis is a minimal collection S of mutually non-adjacent points. Mutually non-adjacent points such that every point of D is either in S or adjacent from a point of S. So there is a slight difference between one basis and the previous concept. A one basis is a minimal collection S of mutually non-adjacent points such that every point of D is either in S or adjacent from a point of S. Okay, so with this concept, what we can say, every digraph has a point basis. Definitely every digraph has a point basis, but not every digraph has a one basis. So converse part may not be true. For example, no odd cycle has one. This is an example. So like this, you can state one result. A criteria for an arbitrary digraph to have a one basis has not yet been found. Okay. So therefore, the theorem statement is every digraph with no odd cycles has a one basis. So these are the statements, results we are considering to understand the concepts properly. The terminology of digraphs we have understood. Based on those terminology, we are trying to understand the results without proof. Okay. Now, so based on this result, there is a corollary. What is that? Every acyclic digraph has one basis. Every acyclic digraph has one basis. Okay. So these are the ideas what we discussed in this session. What are those? We have understood the concept of the converse digraph. So just redirecting, if it is A to B, edge is an A to B, then convert that to B to A. So like that you will get another digraph, that is the converse digraph of the graph D. Okay, vertex set will be same as that of the graph and the converse digraph. Then we have discussed the principle of directional duality. So whatever the concept you are getting the converse digraph, you can generate the results on the converse digraph. So that principle is called the principle of directional duality. So acyclic digraph we have discussed. Next we have discussed a functional digraph. Then point basis of a digraph we have discussed. Later on we have discussed one point basis, and we have considered some results based on these concepts with the in degree, out degree, sink, source, whatever we have discussed, the basic terminology of digraphs. Okay, so these are the few results which we have discussed in this session. So these are the reference books, and with this we conclude this session. Thank you.